Alright, so number 15 is C. 70% of people got that one. 16 is D. Only 37% of people got. 17 was C, 50%. 18 was A, 22%. That was a hard one apparently. 19 is the one they threw out. And we'll come to that second. And then 20 was D, and 41% of people got that one right. Okay, so 15, you have a fraction that you're integrating, and anytime you integrate a fraction, you're going to check and see, is the top the derivative of the bottom? Because if it is, it will integrate to the natural log of the bottom. So in this case, the derivative of the bottom would be 2x, which the top is not 2x, but you can make it be 2x by multiplying by 2 and balancing it with a 1/2 on the outside. So now we do have this. We do have a fraction where the top is the derivative of the bottom. So we're going to keep the 1/2, and then it's the natural log of the bottom plus b. So always check that on a fraction. It won't always work out that way. If it doesn't, then you've got to find some way to rewrite the fraction. If you can make the top of the fraction be the derivative of the bottom, then you can use the natural log to integrate it. Alright, number 16, the combination of a couple of things. Because it has x and y together in the equation, it's not solved for y, it's not y equals, and you can't make it be y equals. You have to do implicit differentiation. Remember, that's where every time you take the derivative of y, you have to put dy dx. Right? And on this side, we have to do the chain rule because sine is on the outside and xy is on the inside. And when we do the derivative of xy, that's the product. So this is hard on a lot of levels. It's hard because it's implicit differentiation. It's hard because it's got chain rule and product rule. So you want to be really careful when you're doing this one. So we're going to take the derivative of both sides. And if we take the derivative of a y, we're going to put dy dx. So the chain rule says we do the derivative of the outside. We leave the inside alone. So we're going to do the derivative of sine, to be cosine. And we're going to leave the inside, the xy, alone. Yeah. It's just the opposite. If you take the derivative of a cofunction, cosine, cosecant, cotangent, that's negative. If you integrate to a cofunction, so if you're integrating and your answer is a cofunction, cosine, cosecant, cotangent, that's negative. So sine, the derivative is positive. And then times the derivative of the inside, and that's where we have to do the product rule, which is first, d last. So first is x, and so we write the x, and then d last, derivative of the y. Derivative of y is 1, but because we're taking the derivative of y, we have to put dy dx. Plus last first equals, and then the derivative of x on the other side is 1. Alright, so the tricky part now is to get the dy dx by itself. Right, that's what we have to do next. So I'm going to distribute the cosine xy to both terms in the parentheses. Remember, terms are separated by a plus sign. So in the parentheses here where we did the product rule, we have two terms. The first d last term, and then the last d first term. So we're going to have x cosine xy dy dx plus y cosine xy equals 1. Okay. We have x times 1 times the cosine of xy, so that'd be x cosine xy dy dx, plus y times 1 is y, cosine xy equals 1. So to get the dy dx by itself, we have to subtract the y cosine xy for both sides. So we're going to get 1 minus y cosine xy and I move this cosine y to the other side by subtracting it. And then we divide by what's in the front of this dxy, which is the x cosine xy. So d, alright.
So we move back to the set before this, so we got equals line minus y cosine xy.
This one? Yeah.
Like, why do that?
I'm trying to get dy dx by itself,
Yeah.
so I have to subtract this term to the other side. You have to get rid of addition first before you get rid of multiplication.
Right, but, okay.
And that's all one term, right?
Yeah.
So I would subtract y cosine xy from both sides.
Yeah.
Does that make sense?
Yeah.
Like I said, that one's tricky. I mean, it has a lot of moving parts, which it, let's see, how many people got that one right?
Did you originally get dy over
37%.
dx from, is that like from
Taking the derivative of y, yeah.
Is the derivative of x just like
Yeah. Dx cancels out. So we don't have to put it. You only have to put it on the y, because dy dx doesn't cancel out. Okay, number 17. The graph of the function f shown above has horizontal tangents at 2 and 5. So they're just letting you know that at 2 and 5 the slope is 0. That's what a horizontal tangent means. It means that at those points the slope is 0. Let g the function defined by, g is the integral of f. So if you would integrate f to get g, that makes this graph the derivative of g. Right? If I integrate a function to get another function, the one I integrated had to be the derivative. Right? So for what values of x does the graph of g have a point of inflection? So remember our little chart, right? If I have the graph of the derivative of g, points of inflection happen anywhere that the second derivative of your function changes sign, and the second derivative is the slope of the first derivative. So for the derivative of g, if I want to know where g has a point of inflection, I need to know where the slope of the derivative of g changes sign. Right? The slope on this graph is the second derivative of g. So that would mean that we would have points of inflection at 2 and at 5. You change from positive slope to negative slope 2, and from negative slope to positive slope to 5.
Okay, I guess I'm really confused. Like, okay, when you're talking about slope, you're looking for when.
So here, let me try explaining it again.
Because I'm looking at like when is the slope, what's the y, what.
Okay, so let's say that we want to know. So here's what the function, the derivative, and the second derivative tell you. Right? The function represents y values of your function. The derivative of your function is slopes of your function. And the second derivative is concavity of your function. Where this gets messed up is when you are not looking at the graph of the function. This is all true when you have the graph of f. When you have the graph of the derivative, all of this gets thrown off by 1. So when I have the graph of the derivative, the y values are the slopes of the derivative graph. And the slopes of the derivative graph are the concavity. So everything goes off by 1. Right? So if I have, when you have the graph of the derivative, here's what happens when you have the graph of the derivative. The y values of the derivative are the slopes of f. And the slopes of the derivative or the concavity of f. So on a function, y values are y values. They're exactly what they should be. Slopes are slopes, concavity is concavity. But when you switch the graph to being the graph of the derivative, then y values now represent slopes, and slopes now represent concavity. Everything bumps down one. And it bumps down again if you do the second derivative. If I do the second derivative, now y values of the second derivative are concavity of the function, because I bumped it down 2 because I'm doing the second derivative. Does that kind of make sense? It was really hard for me to get this when I first started teaching calculus, so I completely sympathize. I'm trying to find a way to say it that will make it make sense. Like, for example, let me give you an example of two functions that you're somewhat familiar with. All right, y equals x squared. Looks like this. All right, this is what the graph y equals x squared looks like. The derivative of y equals x squared would be 2x, right? This graph would look like this. Right? So notice that the original function had negative slope, where the derivative function has negative y. Right? My original function was decreasing and had a negative slope, where its derivative has negative y values.
Okay, so when it had negative x values, it had positive y values, but the slope was decreasing.
Yes.
And we take the derivative of that, where you have negative x values, your slope is increasing, but you have negative.
Right, because the reason that the slope of the derivative is positive is because the original graph is concave up. So if you think about what these represent, slope is rate of change, right? So if I try to figure out what the slope is at negative 2, I would plug negative 2 into here, and I would get negative 4, right? If I want to know the slope of this parabola at negative 2, I would plug negative 2 into the derivative, and I would get negative 4. When you graph the derivative, that slope is the y value on the derivative. Right? And then at negative 1, the slope would be negative 2. So at negative 1, on the derivative graph, we have a y value of negative 2. The slope on this original graph became the y value on the derivative graph. So if I want to know the slopes of my original graph, I have to look at the y values on my derivative graph. Yeah, the slopes on my original graph. It's y values on the derivative. All of these points, the y value represents the slope at each of these points. Does that make sense to some of you? And so, like, a parabola is concave up everywhere, so its derivative has positive slope everywhere, because the slope of the derivative is the concavity of the function. And this graph had negative slope, so it has negative y values on the derivative. It has positive slope, so it has positive y values on the derivative. Had a minimum here because it crossed from negative to positive. Negative slope to positive slope.
Can you do another example?
Let's see. Let me think of a good one.
So, explain the concavity part again.
So the slopes of your derivative graph correlate to the concavity of your function. So since my original function was concave up,
Oh, okay.
then my derivative had positive slope. Right. All right, let's try, we'll do, I want to try to make it kind of easy for me to graph it. So let's do,